This is again a continuation of the Test 3 review. We're going to be looking at Descartes' rule of signs, which is related to polynomial functions. The idea with Descartes' rule of signs is it helps us again to narrow the list of possible zeros, whether or not they're positive or negative at least, so that we can narrow the list. For example, if we use the rational root test here on question 24, although it's not the question that's asked, if we look at that rational root theorem, which is a relationship looking at the constant, which for this problem is 7, in relationship to the lead coefficient, and for problem 24, that is a 5. Let's see. To get 7, we would multiply 1 times 7. To get 5, we can use 1 and 5. So creating our list, we would have 1 compared to 1, 7 compared to 1, 1 compared to 5, and 7 compared to 5. So again, what's happening is we've gone from having a bazillion jillion possible values for x to having 8 options. And we can use Descartes' rule of signs to help us narrow that list even further. Now, they kind of give you the definition of Descartes' rule of signs. It says the number of positive zeros will equal the number of sign changes in the coefficients, or a positive integer less than that number. So basically, what they're saying there, if we think about the positive ones first, is if we look at the polynomial that we're given and we count how many times the sign changes. So let me rewrite this polynomial where we can see it really well, and I can help you count them. We have 5x to the 6th minus 3x to the 4th minus 9x to the 3rd plus 3x squared plus 7. And then I'm going to count the sign changes. Now remember, when there's not a sign written, it's understood to be a positive. So the value in front of this 5 is a plus. So we go from plus to minus. So that's a sign change. There's 1. We go from minus to minus. That's not a sign change. From minus to plus. There's a second sign change. And then it goes plus to plus, which is not a sign change. So there are 2 sign changes. What Descartes' rule of signs says is if there's 2 sign changes, that means you could have 2 positive zeros or a positive integer less than that. So basically you have to subtract 2 from the 2 sign changes. We could have 0 positive zeros. So based on the sign changes, in using Descartes' rule of signs, we could either have 2 or 0 positive zeros. Then to consider whether or not you have negative zeros, you take, and instead of using the original function, we substitute negative x into the function all the way across. So we would have 5 times negative x to the 6th minus 3 negative x to the 4th minus 9 negative x to the 3rd plus 3 negative x squared plus 7. You have to work that out. Anytime a negative is raised to an even exponent, it comes out to be positive. So this is still going to be 5x to the 6th minus 3x to the 4th plus 9x cubed. Think about it. Negative x times negative x is positive x squared times negative x is negative x cubed times negative 9 is positive 9x cubed plus 3x squared plus 7. Once you get that calculated, again, what you need to do at that point is to count the sign changes. Again, remember that the sign in front of the 5 is a positive. It's understood. So from positive to negative, there's a sign change. From negative to positive, there's another sign change. Then it goes positive to positive, no sign change. Positive to positive, no sign change. So again, we have 2 sign changes. So in this particular scenario, we would have 2 negative zeros, or again, remember to subtract 2, 0, positive, not positive, but negative zeros. Okay, so 0, negative zeros. Okay, and remember that the degree, or the highest exponent, tells you how many zeros you should have. So if I have 2 positive and 2 negative, then there's 2 that are outstanding, and most likely I would anticipate that those are imaginary solutions. Again, it doesn't tell me what the solutions are, but it tells me how many to look for. So I know when I found 2 positive zeros, I can stop looking for positive ones. Or when I find 2 negatives, I can stop looking for negative ones. All right, we're going to shift gears now, and they changed topics here for the last few problems, and they begin talking about rational functions. Again, they really don't define for you, at least not here on the review, what a rational function is. And basically, a rational function is one that looks like a fraction. So you have basically some polynomial in the numerator, which is the top, and you have another polynomial in the denominator, which is the bottom, so that it looks like a fraction. So when you have a function that looks somewhat like a fraction with a polynomial in the numerator and denominator, you have a rational function. One of the things you have to be careful about with rational functions is remember that you can never have 0 in the denominator of a fraction. And so we have to be careful about that when we're dealing with those functions. And basically what happens is we have to avoid the value that makes the denominator 0. And to do that visually on the graph, we use what's called an asymptote, specifically a vertical asymptote that runs up and down. And the way you find that is you simplify your rational expression, if it's possible, and then you make sure that you don't choose a value that makes the denominator 0. So I want to try to simplify this particular polynomial first. And to do that, we have to factor. So x squared minus 4 does factor into x plus 2, x minus 2. In the denominator, it factors into x 2 and 1. It's going to be plus and plus. So this one actually does simplify here because I have an x plus 2 in the numerator and an x plus 2 in denominator. Now, we have to avoid the value that would make x plus 2 negative, but they don't talk about that here. It's actually called a point of discontinuity. So once we've simplified it, we have the rational expression x minus 2 over x minus 1. And we want to avoid the denominator being equal to 0. So if I take the denominator, which happens to be x minus 1, and I set it to 0 and solve by adding 1 to each side, I have x equals positive 1. And that value of positive 1 is our restriction, or the value we have to avoid. And so this is where our vertical asymptote would occur on our graph. We would have a vertical asymptote at the value that makes the denominator 0. Finding the horizontal asymptote is a little bit more complicated, and I don't know if I have time to do it in this video, so I'm going to try to make one more and finish up this review sheet.